calculated by lowercase q, the flow rate per unit width divided by the depth. For a trapezoidal channel, it might be easier if you put in a column for the area and the wetted perimeter for the trapezoidal channel, and then just calculate the velocity as q over a. And if you put in an equation or a column for the area and wetted perimeter, then you can just calculate the hydraulic radius. In this spreadsheet, what I have in this column is the formula for the area and the formula for the wetted perimeter. That's what was in there. It's going to be easier for the trapezoid if you just make those separate. And what as I said, is you start at the known depth, kind of the control depth. And for the direct step method, you take a guess at what the upstream depth is, and then through the calculations, calculate the distance that it takes to get to that change in depth. Okay, so you're calculating delta x. This method is sort of like Euler's in a way, Euler's method, and that is, it's kind of sensitive to what you assume for the change in depth. So I said, let's start at 10 feet and go to 9.9. That's a pretty small change, okay? But this is kind of like the step size in Euler. So if you have too large of a step size, there's going to be lots of error, right? So smaller step size is better. And I guess for this 1/10 of a foot in depth, the distance was 1,000 feet. So it's quite a long ways. So all these calculations up to this point are kind of easy, and where you see a mean velocity and a mean hydraulic radius, we're taking the average of those because we're assuming within that delta x that we're calculating, we're going to treat that channel as a uniform flow. And to get the mean velocity and mean hydraulic depth, we take the mean, and then remember over here for the slope of the energy gradient, where did remember last time I showed you, do you remember where did the equation for SE come from? Anybody remember? Well, suppose I ask you this question on a quiz. If we have uniform flow, and you want to know the slope of the energy gradient, how do you calculate it? I have one person here that says for mayonnaise. Does that make sense? Tough crowd today. So if we have mayonnaise, this is the way mayonnaise is usually graded. S0 is what? It's the slope of the channel. And I want to know the slope of the energy gradient. Is it the same or different than this? It's the same. And it's the same because in uniform flow, if here's the bottom of the channel, the depth is the same throughout that, so it's parallel to it. And the velocity is the same in that section of the channel. So on top of this, there's just going to be a little bit of v squared over 2g. So in other words, this is S0. Here's the water surface, which is parallel to this. And then, because velocity is the same in uniform flow, above this is going to be something that represents v squared over 2g. And that's going to be parallel to it. So this also, in uniform flow, is the slope of the energy gradient. Okay? So SE in that is just a rearrangement of the mayonnaise to solve for this. And then once you know that, you can calculate the specific energy, which is just the depth divided by v squared over 2g, and then you calculate delta x, and delta x is from the formula from that's in the notes. Delta x is from this. Okay? So pretty straightforward. Here's the project. So it says, as part of a stream restoration project, your firm has been asked to perform some hydraulic calculations for the scenic river. Just as an aside, what is stream restoration? Well, what it means is in the environmental field today, this is actually sort of an area of a lot of job growth. And what it means is, over the years when we've implemented laws to clean up pollution, what we haven't done lots of times is to restore the integrity of the stream in terms of, a lot of our streams have been channelized, right? We, built roads next to them and we have bank erosion going on. So stream restoration seeks to restore sort of the physical and ecological integrity of the stream in addition to just cleaning up the pollution, okay? So a lot of work in this area, actually. So it says as part of this process that you're asked to perform some hydraulic calculations. The sections of interest are upstream of an abandoned low-head hydro dam. Well, what is that? You see a lot of these actually out there in the field, and at one time when hydro started to become implemented, that there were a lot of these low-head hydro dams built. So not like the Hoover Dam, but something that may be 4 or 5 feet in height, right? And so they put a dam in, and without height of water, they use that low head to generate some small amount of hydropower. And a lot of these became abandoned, right? They weren't economical anymore, but they still exist. And part of the stream restoration is oftentimes to say, gee, we'd like to remove this old dam and allow fish to then migrate upstream and spawn and that sort of stuff. Okay. The dam is 4 feet in height and acts as a broad-crested weir. Okay, so this is where kind of weirs fit into this. Section 1 of the stream is upstream of the dam. The characteristics of section 1 are as follows. So it's trapezoidal, bottom of 75 feet. Side slope, vertical to horizontal is 1 to 3. Pitch, Manning's N is given. The bottom slope of the stream bed, 0.001. Bank full depth is 8 feet. What is bank full depth? This is a term that's used in stream restoration a lot. And it means if you had a trapezoidal channel like this, it means just what the words say. If you're right to the top of the bank, that's where the water is. That's referred to as bank full depth. So in this problem, that's it. Okay? In this flow is of interest because it's related to the channel forming characteristics of the stream. So when you see a stream that has certain meanders and certain morphology and so forth, it's related or can be related a lot to this bank flow, flow. Discharge is 1,000 CFS, and the length of that section is 2 miles. Section 2 is upstream of section 1 and has the same geometry as section 1, except that the bottom slope is 0.006. Okay? So I guess our stream sections look like we have something like this, then a shallower channel, and then this dam here, and that's 4 feet in height. The calculations and deliverables are as follows. 1, the normal depth for each channel section at 1,000 CFS indicate whether the flow is subcritical, critical, or supercritical. Bank full discharge at each section based on Manning's equation. So I've told you what the bank full depth is, and then I just want you to calculate what the discharge would be. Bank full discharge with the dam in place. Channel at the dam can be considered rectangular. Let's see, bottom width 75 feet. So we have a dam, and let's suppose that right at the dam, oftentimes these dams are built in sort of a gorge area anyway.